All right. Good morning, everybody. So today is going to be our last lecture of the semester. So let's finish this up. On Friday, we will have in-class assignment, and then our final exam schedule for next Wednesday. So at the end of the lecture, I will give you some more instructions about the final exam, and I will also post the instructions on Canvas. Then you have it there if you want to check it later. Okay, so for today, we will tackle chapter number 10. So in this chapter, we will study how molecules interact with themselves. And the title for this chapter, therefore, is Intermolecular Forces. So very short chapter. We will cover the different kinds of intermolecular forces. And then we will use that for correlating intermolecular forces with boiling point and a little bit of polarity and solubility as well. So it's a very, very short chapter, should be very simple. So let's start it then. Okay, so different molecules, they will interact with themselves based on some properties from each molecule. So I will show you the different intermolecular forces, starting from the strongest and moving all the way to the weakest intermolecular forces that are possible. So let me switch to my other screen really quick here. Okay, starting with ion-ion forces. Ion-ion forces are going to exist when you have two or more ions with opposite charge interacting with themselves. So therefore, is based on the interaction between ions, and it is a very strong interaction. Actually, it is the strongest interaction possible. So for example, here, sodium chloride. We know now that sodium chloride is formed by sodium plus and Cl minus, which is chloride. So therefore, we have ions with signs that have opposite sign. Therefore, the interaction between a Cl minus and a sodium plus ion, I'm going to represent here by the double arrow. This interaction here is called ion-ion interaction. So every time we have a cation and an anion, we will have ion-ion interaction. And this is the interaction that keeps the solid structure as it is, okay? And again, this is the strongest interaction that we can have. Okay, so now let's move on to the second one in the rank for intermolecular interactions. And this is a very special interaction called hydrogen bonding. It is an intermolecular interaction between two or more molecules where there is hydrogen bonded to fluorine, oxygen, or nitrogen, based on the interaction between strongly positive charged hydrogens and strongly negative charged fluorine, oxygen, or nitrogen. It is a strong interaction. So let's see how the hydrogen bonding works. So let's have here as our example, the water molecule. Let's remember the electronegativity scale. So we start with fluorine, the most electronegative element, followed by oxygen, nitrogen, chlorine, bromine, iodine, sulfur, and then carbon, almost the same as phosphorus, almost the same as hydrogen. Okay. So this is the most electronegative element, and on the other side, the least electronegative element. Because the electronegativity difference between fluorine and hydrogen, oxygen and hydrogen, and nitrogen and hydrogen is really high, that means the oxygen atom bonded to the hydrogen is extremely negative, and this hydrogen is extremely positive. It's not a charge by itself, but it's really close to a positive and negative charge that is resulted from the high electronegative difference. So therefore, we create here a very strong dipole, and that causes this hydrogen, which is very positive, to interact with the oxygen from another water molecule. So the positive pole here will interact with the oxygen from another water molecule. And this special case here is called hydrogen bonding. And pay attention to one detail here. We must have a hydrogen bonded to fluorine, oxygen, or nitrogen to be able to do a hydrogen bonding. Okay. Another example of hydrogen bonding would be between ammonia molecules. So ammonia is NH3. So again, we have nitrogen bonded to hydrogen because we have a huge electronegativity difference. The nitrogen is going to be strongly negative and the hydrogen is strongly positive. And that will create a very strong dipole here, allowing the interaction between the hydrogen with another nitrogen from a neighbor ammonia molecule. And therefore, when we have hydrogen bonded to fluorine, oxygen, or nitrogen interacting with fluorine, oxygen, or nitrogen, we have again here hydrogen bonding. So this is a strong interaction and is the second one in the rank of strength for the intermolecular interactions. Okay, so see here that the strongest interaction is when we have two very well-defined charges, one positive and one negative. The second one is when we have almost a charge, something very close to a positive and negative charge, but still not well-defined. So now let's move on to the third one in the rank. And the third one is called ion dipole forces. It is an intermolecular interaction between a polar molecule and an ion. It's based on the interaction between dipoles and ions. And it is a strong to very strong interaction. So in this case, we are going to have an ion that can be a cation or an anion. And this charge is going to interact with a dipole. So the example here that we are going to take a look is sodium dissolved in water. So let's draw here the water molecule again. So this is a polar molecule because the resulting dipole vector is different from zero. We know here that oxygen is the is the negative pole of the molecule, and hydrogen is the positive one, and that's caused because of the electronegativity difference. So therefore, the water molecule is polarized. Okay, negative pole is located nearby the oxygen. That means excess of electrons there. And the positive poles are located nearby the hydrogens, meaning electron deficiency over there. When we have sodium plus dissolved in water, all of a sudden we have a positive charge. And we know that the positive charges will attract the negative charges close to itself. So therefore, the negative part of the water molecule is going to align here with the cation. Okay, so therefore we have the oxygen strongly interacting with sodium plus. So a dipole interacting with a charge. And this sort of interaction is called ion dipole interaction. And this interaction can range from strong to very strong interaction. All right, let's move on here. Okay, so now let's start talking about the strong to moderate interactions, starting here with dipole-dipole interactions. It is an intermolecular interaction between two or more polar molecules. Okay, attention to that detail. Based on the interaction between the dipoles of polar molecules, and this is a moderate to strong interaction. So let's see here the example of the dimethyl ether. Again, remember the electronegativity scale, because that will help us to determine if first a covalent bond is polar, and then second, if the whole molecule has a dipole moment different from zero. We start analyzing the polarity of the bonds, drawing the vectors, and then taking into account the geometry, we are going to determine if the resulting vector is zero or different from zero. If it is zero, molecule is nonpolar, different from zero is polar. Okay, let's look here at the dimethyl ether. Dimethyl ether is H3C bonded to oxygen and then bonded to another H3C group. Okay, so this is an angular shaped or V-shaped or bent molecule. So therefore, it is a polar molecule. We know here that carbon and hydrogen, they have kind of the same electronegativity, so nothing will change for carbon and hydrogen. However, carbon and oxygen, there is a huge electronegativity difference, which means we will have accumulation of electrons nearby the oxygen and deficiency of electrons at the CH3 group. And that's what this picture is showing right here. So the red area here means high density of electrons, and the yellow-green area means deficiency of electrons. So therefore, the dimethyl ether molecule has a negative pole nearby the oxygen and positive poles nearby the CH3 groups. This is not a charge by itself, a well-defined charge, but it's something very close to that. So therefore, the negative part of the molecule will interact with the positive part of a neighbor molecule. Oops. Right here. And this kind of interaction is called dipole-dipole interaction. Okay, two opposite poles interacting between themselves. Attention, because we need to have two polar molecules interacting. Okay, so very careful to don't make the mistake and think that we have a hydrogen bonding here. Okay, to be a hydrogen bonding, the hydrogen needs to be bonded directly to fluorine, oxygen, or nitrogen. Okay, otherwise you cannot have hydrogen bonding. And in this case, we have hydrogen bonded to carbon. And because of that, this cannot be a hydrogen bonding. Okay, very good. All right. So now what's left here is the weakest interaction possible between molecules. And this interaction will be the last one that we are going to tackle here. Is called dispersion forces, or also called London forces or van der Waals interactions. It is the predominant intermolecular interaction between two or more non-polar molecules. And it is based on the creation of induced dipoles due to the uneven movement of the electron cloud. It is a very weak interaction and also called van der Waals interactions. Okay, so let's do here a quick recap. We started with the strongest interactions. In the case when you have two well-defined charges, a positive and a negative, and then we moved down the scale when molecules did not have a charge by itself, but something very close to that. And of course, the weakest interaction possible is when you don't have a charge or anything that resembles a charge, therefore a nonpolar molecules. Nonpolar molecules, they do not have a well-defined positive and negative dipole. So let's see how that works. So let's look here at the ClCl molecule as our example. There is only way to arrange two atoms, and that is in a linear fashion. Because they are the same element, there is no difference in the electronegativity, which means that this pair of electrons is being equally shared between the two atoms. So if we could take a picture of the electron cloud for this molecule, we would see a very even electron distribution, okay? So we have here the two nuclei and the electrons being equally shared, okay? So if they are equally shared, there is no deficiency or increasing in the electron density. However, keep in mind that the electrons are not static, so they are moving all the time. And then, for some reason, at a very small fraction of time, we may have a slight accumulation of the electron cloud in one side of the molecule, creating a very small delta minus and delta plus. So that creates instant polarization of the molecule, and that will allow this molecule to interact with another molecule where the opposite is happening. And this kind of interaction is going to be called dispersion forces or London forces or van der Waals interaction. Okay. So this kind of interaction is caused by the movement of the electron cloud that can create a very small dipole in a fraction of time, and that will allow the interaction between two non-polar molecules. Because this kind of interaction depends on the movement of electrons, if you have larger molecules, there is a higher probability of creating these instantaneous dipoles. Therefore, larger molecules have more intense London forces. The reason for that is because it is easier to mess up the electron cloud when you have a large molecule, more freedom of movement as opposite to a small molecule where things are more constrained. All right. Okay, so next slide uh, shows all the interactions that, not all the ones that we talked, but most of them. So it's missing here the ion-ion interaction, which would be the strongest one. But then here we have ion dipole, hydrogen bonding, dipole. We can have dipole-induced dipole, interaction between a polar and non-polar molecule, and then dispersion forces, which is the interaction between non-polar molecules. And see here how the size affects strongly the dispersion forces. For example, here, if you move from chlorine to towards the iodine, you increase the size, and that results in stronger intermolecular interactions. Therefore, ClCl is a gas at room temperature, bromine is a liquid, and iodine becomes a solid. Okay, so larger the size, stronger is the dispersion forces, and that causes a difference in the physical state at room temperature. Okay, so let me switch back to the PowerPoint. Okay, intermolecular interactions, they have a strong influence on melting point and boiling point of chemical compounds. Stronger the intermolecular interaction, that will reflect in a high melting point or high boiling point. So try to picture that in the solid state, the molecules are strongly interacting. When you want to move to solid state, for example, to liquid state, you need to get the molecules and take them far apart. Okay, so you need to overcome the intermolecular interactions. And moving from liquid to gas, you need to break completely the intermolecular interaction and eject the molecules to the air. Therefore, higher intermolecular interactions will reflect in higher melting points and boiling points. And here we are always comparing two or more things to establish a scale going towards the highest to the lowest or vice versa. The melting point and boiling points are directly correlated with the intermolecular forces. Stronger the interaction, higher the melting and boiling points. For example, the boiling point of water is 100 degrees, while of hydrogen sulfide is minus 60 degrees. Oxygen and sulfur, they belong to the same group in the periodic table. They have the same molecular geometry. However, water has a higher boiling point than H2S. What's the reason for that? Well, when we have hydrogen bonded to oxygen, we can have hydrogen bonding, while hydrogen bonded to sulfur cannot establish hydrogen bonding. And hydrogen bonding is one of the strongest intermolecular interactions. That means the water molecules are, they have a very strong bonding between themselves, and it's hard to separate two or more water molecules. And that reflects in a higher boiling point comparing the two compounds. Hydrogen bonding is very important in biological systems. And the classic example here is the DNA double helix. This structure is only possible because of hydrogen bonding. So when we have two nitrogenated bases interacting between themselves, we see here that we have a hydrogen bonded to a nitrogen. So therefore, this hydrogen can make a hydrogen bonding with another atom of nitrogen. And that happens here at the top of the structure as well. Another hydrogen bonded to a nitrogen. Therefore, this hydrogen can do hydrogen bonding with the oxygen here on the top of the other nitrogenated bases. Adenine and thymine, they do two hydrogen bonds, and G and T, they can do three hydrogen bonds. Okay, and that's one of the reasons that the helix is tweaked. Okay, so stronger interactions here and strong here, but not strong as the bottom one. So therefore, hydrogen bonding is what it keeps the DNA bonded. Okay, the two strains bonded. So when you wanna split the two strains, you have to break here the hydrogen bonds. Okay, so that's how you unzip the DNA and can do all the biological processes. Okay, so water is a very special case because it has strong intermolecular hydrogen bonds, and uh, the result of these very strong hydrogen bonds when you have water is a high surface tension. Okay, so because uh, the hydrogen bonds are so strong in the surface of the water, it creates kind of a thin layer that can support, for example, small animals. So because they are very light, they can stand on the water and they will not break the hydrogen bonds and they can flotate on the water. We are not going to talk about this. Okay, and then to finish up, let's talk a little bit, just a little bit about the effect that addition of sodium chloride has to the boiling point of the water, for example. Okay, so let's first try to visualize what happens when you are boiling a solvent, for example, water. So if you have water here, that's of course an exaggeration of what happens, but you have water molecules very close to the surface. If you heat the water, that will increase the temperature, increase the movement of the water, and eventually some of these molecules will come out of the liquid and go towards the air, okay? And then new molecules will come here and that will repeat itself. So when that is happening, we have here a boiling or evaporating the water, okay? So therefore, for the water to be evaporated or boiled, the molecules, they have to come out of the liquid and go to the air. For that to happen, we have to break the hydrogen bonding between two molecules. So what would happen when we add, for example, sodium chloride to the water? Well, when you have sodium chloride in the water, you are going to have a cation and an anion. Therefore, two well-defined charges. The positive charge is going to be able to attract the negative part of the water. So all the oxygens will turn to the sodium plus, and all the hydrogens will turn to the Cl minus. And here what we are going to establish is a very strong ion dipole interaction. This interaction is so strong that now we need more energy to disconnect the water molecules from the ions to boil them. Therefore, when we add a salt to the water, the result will be an increase in the boiling point because we are increasing the strength of the intermolecular interactions. The effect on the melting point is going to be a decrease in the melting point because now it's harder to get the water molecules together to crash out as a solid. Okay, So therefore, addition of salt to the water increases the boiling point and decreases the melting point. And that is the basis for all the colligative properties that unfortunately we didn't have time to talk about, but you're going to see something tomorrow for your lab. Okay, go back to the PowerPoint. Okay, so at this point, doesn't make sense to start anything new. Should finish this course on chapter 11. So let me talk really quick about the final exam that will take place on May 12. So our scheduled time is from 8 to 9:50. The exam will be available on Canvas as an assignment at 7:50, so 10 minutes before they start. And between 8 and 9:50, I will be available on Zoom, the same link as the lectures. If you have any questions about any of the questions in the exam or anything else. What's the format? The final exam will have 30 questions, all multiple choices, and there is one and only one correct answer. What I want you to do is to just submit in the assignment, the answer sheet with your name in it and the answer for each question. No need to show any calculation for the final exam. So let me show you what the answer sheet will look like. Just a second. Okay. So this is what the answer sheet will look like. Of course, this here is for the last semester. So I just need you to put your name, and then for each question, you're going to put your answer here, A, B, C, or D. You can either print this page and fill up the answers, or just write the answers in a sheet of paper, scan it, and submit it. Doesn't matter. I just need your name and the answers for each question. Okay, so with that being said, I think that's where I will end for the semester. So we will still have in-class assignment on Friday and then the final exam next week, and then that will be it. Okay, so I hope you have a good luck for your finals, and if you need anything, just let me know. Bye-bye.
Thank you, George.
Bye. Thank you, Professor.
Thank you, Professor.
George.
Thank you, Professor.
Thanks, Professor.
Thank you. Have a nice day.
Have a good day. Have a good break. Just, yeah.
Yeah, we all need it.